Right. Okay.
All right, everyone, we're going to get started here. All right, thank you all for joining us today for the HMSC Research Seminar. My name is Yi-Chung Chung. I am the Academic Program Manager at Oregon State University's Hatfield Marine Science Center here in Newport, Oregon. And I will be your host for today's talk. Just a reminder, this is a hybrid event, and folks attending both on-site and online. Roseanne is our hybrid support today. Please let her know if you have any technical issues so she can assist, or let those of us on site know. For those of you online, we have your mics, cameras, and screen share off. But please ask any questions you might have using the chat at any time, and we will answer any questions at the end of the talk. If you put a question in the chat, we will also read it out for everyone. You're also welcome to raise your digital hand at the end of today's talk, and we will be letting you know when it's your turn, and we'll help to unmute your mic. For those in the room, if you're not already, please make sure you sign in, and if you haven't, sign in on the way out. We will be handling questions today at the end of the talk. Again, raise your hand here, and we'll bring the mic to you so that when you do ask your question, the folks online can hear your question. We will be recording this event, and it will be posted on the HMSC past seminar page in a few days. And if you're not aware, we also have a YouTube channel. All right, so some quick announcements. Our next Science on Tap is this Wednesday, November 15th, when Suzanne Brander will be talking about plastics in the environment, impacts on organisms in Oregon and beyond. The social hour starts at 5 and the talk starts at 6 here in the Gladys Valley Marine Studies Building auditorium, also online. Also, for next week's research seminar on November 16th, Nicholas Batista, School of Science, College of New Jersey, will talk to us about fish, worms, and beyond, using computational models to study how variations in morphology and kinematics affect swimming performance. So at this point, I would like to hand the mic off to Bill Chadwick to introduce today's speaker. Bill is an oceanographer and former program manager of NOAA's Pacific Marine Environmental Laboratories Earth-Ocean Interactions Program, and is currently the research associate for in the OSU Cooperative Institute for Marine Ecosystem Resource Studies.
Okay, thanks everybody for coming. Today's speaker is Harvey Kelsey. He's a research associate in the Department of Geology at Cal Poly Humboldt in Northern California. He got his bachelor's in geology from Princeton and a PhD in geology from UC Santa Cruz back in the Pleistocene, in his own words. After that, he worked at Redwood National Park for several years, and then started an academic career that took him to Western Washington University, Cal State Humboldt, which is now Cal Poly Humboldt, and he's also is affiliate faculty at University of Washington. His specialty is in recent active tectonics and finding evidence of recent earthquake fault movements in coastal and river drainage landscapes. He's worked all over the world and up and down the West Coast. Today he's going to talk to us about the evidence for an active fault in our own Yaquina Bay and its history of movement. So we're all familiar with the earthquake hazard from the Cascadia subduction zone, which is far offshore and deep under our feet. But this fault represents a much different kind of hazard, since the fault is in our backyard and comes all the way to the surface. So take it away, Harvey. Thank you.
Thank you, Bill. I'm going to make sure I know how to advance slides. Yes, I do. Okay. Well, it's a joy and a privilege to be in this new building. I've never been here before. I off and on have gone through these facilities, and when I was doing my initial work up in the in the marine terraces in the Yaquina Bay area. I've lived in some of the housing here, and one of my graduate students lived here for a while. So it's returning to a place that was part of our original work. Okay, well, as the slide says, I'm going to talk to you about evidence for recent displacement across the Yaquina Bay Fault and another fault nearby. And this is occasioned by new results for technique for age determination called luminescence dating, and looking at the morphology of coastal terraces. And first, I want to thank my collaborators. Science today, more than ever, is very much a collaborative effort. Different people have different expertises. And much of what I'm going to discuss today is work I've done in collaboration with Kirsty McKenzie, Kevin Furlong, and Eric Kirby. And part of this work was recently published in the Quaternary Science Reviews, and it was I sent this article to Bill because I thought he'd be interested, and that occasioned him inviting me to give a talk, and it took several years or a year and a half for us to get to that point, but we did. Also, I'd like to thank other collaborators. The National Science Foundation has supported this work on 3 separate occasions. Jim Bachheim is a soil scientist at the University of Wisconsin and was very instrumental in working with me on initially studying the marine terraces here. And Rob Tickner was a former grad student who worked on this, specifically in this area, and he spent 3 or 4 weeks living in housing here just on this campus as while he was doing this work. And this work, the original work on marine terraces, was published in the Geological Society of America Bulletin in 1996. So we've basically revisited an area that Gulp we first published on 27 years ago. So it's been a longstanding love of mine in terms of science. Well, here's a roadmap of my talk. I'm first going to discuss briefly the geologic setting, and then I'm going to discuss the structure of subduction zones as they would relate to the problem I'm going to put forward to you. And then I'm going to talk about marine terraces for an extended period of time, how they're formed, the faulting and folding that occurs on them, and more recently, how we've determined ages of marine terraces. Marine terraces are important. They're the tools by which we understand the deformation that has occurred here. And then I'm going to talk about fault slip rates, which I'll define what those are, on the Yaquina Bay Fault and the Thiel Creek Fault. And finally, I'll merge into a discussion of seismic hazard. We're getting right down to the geologic setting. The western margin of North America is entirely a plate boundary. To the south of the Cape Mendocino, it's the boundary between the Pacific Plate and the North American Plate, separated by the infamous San Andreas Fault. And north of the Cape Mendocino, the boundary is the Cascadia subduction zone, and under which the Juan de Fuca Plate is subducting beneath the North American Plate. And we'll talk certainly more about that. This is a schematic of what the Cascadia subduction zone looks like in its entirety. It extends from south of Cape Mendocino all the way up to the north of Vancouver Island. And we're going to focus in on this red framed area here. And just to point out that you can see let's see, I have a pointer here. There we go. So this black line here is, oops, I'm not going to be very agile with this pointer, but this that black line there is the subduction zone. And that's where the subduction zone merges upward onto the seafloor. And that subduction zone is the boundary between the plate that's going underneath and the plate that's on top. And the place on top is what's called the upper plate, and subducting plate is the oceanic plate. And here I show this in the context of Newport, the red star here, and the Yaquina Bay Fault on the right panel. Now, I'm going to talk in a little more detail about structures of subduction zones as it relates to the problems that I'm going to be presenting. So here's a cartoon, which some of you may be familiar with, but it's simply to emphasize the lower panel shows what happens during an earthquake, co-seismic deformation. So the upper plate leaps forward and abruptly transitions, slides over the lower plate, and that's what causes seismic shaking, and offshore would cause a tsunami. But most of the time, we're between earthquakes, and we're in what's called the interseismic deformation. In that case, the lower plate and the upper plate are locked, but the lower plate's still subducting underneath the continental plate. So you get slow, gradual deformation in the overlying plate. That's depicted by the green area there. But I'm going to add, so let's first look at this map again. And I just want to point out to you that these vertical lines here are the contour lines of how far down below the land surface is the subducting plate. For instance, Newport here is, if you could read these contour lines, it's not important that you can, because I can. The lower plate is about 25, 30 kilometers below us. 25 or 30 kilometers right below us is this big mega thrust. And of course, as you go offshore, it's going to daylight, so to speak, or reach the surface at the subduction zone. Now, a couple other things to remind myself where I'm going here. Yeah, a couple other things to note about this map here is that, first, look at offshore. This is a digital elevation model. It shows that the offshore bathymetry in the upper plate is very rugged. It's full of folds and faults, and the upper plate is not just a simple plate that is riding over the lower plate. Plus the fact, if we look at this digital elevation model in this gray shaded area on the right panel, you can see that there's the coast range. We all know there's a coast range. Well, if we go back to our simple diagram, there's two exceptions to the simple diagram. First off, the subduction zone is not elastic. That is, it simply doesn't come back to its same shape every time, although that's the model. It's been proposed that you get an earthquake, then there'll be strain that would build up, and you get another earthquake, and that would reduce the strain, release the strain, and the earthquake would occur, and then the strain would accumulate again, and you'd never have any change. But you do have change. The subduction zones are inelastic. That is, they have permanent uplift, and that is manifest by the fact that we have the coast ranges, and it's also manifest by the fact that we have these upper plate faults. And that's the other thing, is a simple subduction zone model, you just have the subduction zone megathrust. And that's the emphasis what's been put on. But really, there are lots of what are called faults, upper plate faults. There are faults in the upper plate, and I've schematically shown by this red line one of these upper plate faults. And we are today going to be more focused on what's happening in the upper plate, recognizing that, of course, the subduction zones is where the main earthquakes ultimately occur. And I want this point, rather than introducing this at the beginning, it's more pertinent to introduce this concept now. We've talked about subduction zone for a second, but as with each earthquake, major earthquake that occurs on Earth, seismologists and earthquake geologists go out and study them in detail and find what's going on. And we learn a tremendous amount from each large earthquake. They're tragic in one sense, but they're in a very real sense, but they're also very informative. And we've learned a lot about the recent deformation at plate boundaries from these earthquakes, and most notably in this case, the Kaikoura earthquake, which was a magnitude 7.0 earthquake that occurred in November of 2016 in New Zealand. And it was shocking in many ways. It was a subduction zone event. Part of the subduction zone ruptured, but there were also numerous faults in the upper plate, and these faults moved as much as 5 to 10 meters. That's a lot for a fault to move at once. And the faults were in various directions. Most of them were strike slip, but when two strike slip faults were intersected at an angle, then there would be some what are called thrust faults that would occur. And it was a damaging and very surprising earthquake. And it made us think the subduction zone earthquake community, was this an odd thing, or do these sorts of unexpected pervasive damage and deformation to the upper plate, does that occur during other subduction zone events? And people started to think about that, and there are other places where the answer would be yes. But what was interesting about coming back to Newport is that working with Kirsty McKenzie, and this was primarily her research, as part of her PhD, she started looking in more detail at the faults locally. And so, so this talk is going to largely be a combination of the work we did back in the 1990s, looking at how these marine terraces and initial deformation, and then what Kirsty, in collaboration with the rest of us, have learned about looking at these faults with a new eye. But in all cases, we've learned from these faults through marine terraces. They are the tool that we use to assess deformation. So I'm first going to talk about how marine terraces are formed. And probably with very little doubt, you live on marine terrace. You certainly, when you're in downtown Newport or South Beach, you are on a marine terrace. They're ubiquitous to your life. Marine terraces are formed at sea level, and they provide a benchmark indicating present sea level or past sea level if they're preserved in a landscape. And they're simply the benchmark is where if you're at the beach, where the beach intersects the sea cliff, and that is an indication of the ocean, the sea level at that time. But you can also have this intersection of raised beaches with the paleo sea cliffs, old sea cliffs, which can indicate sea level at former times. And this was first became apparent when people started trying to interpret landscapes like this. This is in Papua New Guinea, and these horizontal lines are indicators of former sea level, and they're coral reefs, because in warm tropical areas, rather than having bedrock carved platforms like we have, coral grows at sea level. And each of these horizontal lines is a time of present sea level, which was preserved because of rapid tectonic uplift rates of this particular part of New Guinea. Now, based on this, one of the initial people who went here said, hey, we know that glaciers come and go, but there's actually a signal of glaciers on the landscape through these marine terraces. That is, marine terraces can be used to put together a sea level curve. Sometimes sea level is high, sometimes it's low. It's high when all the water there's very little water incorporated in the glacial ice. Sea level is low during glacial periods when a lot of the water is taken out of the ocean basins and put into ice on land. And so you get a series of high stands and low stands, and obviously this would be a high stand of sea level, and that would be a low stand of sea level, and high stand and low stand, and that became and the realization became more and more apparent that where you had uplifted terraces, it was telling you something about sea level, and in reverse, sea level was telling you something about uplift rate. So here's that same curve I just showed you a second ago. Now, let's suppose you're at a landscape or a portion of the coast where there's no tectonic uplift. This basically just stasis. Then what's going to happen is you're going to, at high stands, when there are non-glacial periods, you're going to get sea level at its highest level, and it's going to erode, in our case, would erode the bedrock platform. And then next glacial period, with a lot of water is incorporated in ice, sea level will drop, and then when next interglacial comes, when the glaciers all melt, sea level will come up again. And if there's been no uplift, then it's just going to erase what was there before and start over again. So you have this erosion at sea level, drop from the high stand, come up again, erode at the same level, and you would never see any indication that there was a variation in sea level over time. However, where there's an uplift rate, then it's very different. Imagine you have we'll use a coral reef, and for this example, it's really the same difference as shoreline. You have a coral reef that's formed at sea level, and then sea level drops during glacial period, but it's a high eroding area coast. By the time sea level comes up again, that coral reef's been uplifted out of harm's way, so to speak, and so it gets preserved on a landscape. And if you do this over and over and over again, you get a sequence of marine terraces. And if there's a constant uplift rate, then you can, or even if there's not, but the uplift rate will determine how high the terraces are and how many terraces there are. So that's the fundamental principle upon which we understand and use marine terraces. And so, does anybody have a question about how this works? Because this is. Yeah, and the exact process is debated, but yes, the uplift around here occurs because of this recurrent subduction zone earthquakes and this sort of non-complete recovery. The fact that the subduction zone is so-called inelastic. Anything else? Here? Yeah, well, yeah, so this example here is 0.7 meters per 1,000 years, and that's a good question because what I'm going to show you as we go on is the rate's really variable. It's not only variable in any one space, but over time. And that's one of the interesting things is since we can get this rate, we can then look at the variation. So, but yeah, in general, the rates could be as high as low as rather than 0.75, the rates could be as low as less than 0.1 meters per year, or they could be as high as 3 or 4, 5 meters per year. So this is, in this case, it's an uplift rate. But I'm also going to talk about, as we go on the coast, to talk more about slip rates, and those are different sort of rates on faults. So this beautiful photograph is a picture of marine terraces on San Clemente Island in Southern California. The reason I show it is because this is a very arid area, and you can see these terraces beautifully on the landscape. You can see the modern shore erosion occurring, and where there's a sea cliff against the bedrock shoreline. And then you can see in this case, there's at least 1, 2, 3, 4, 5, 6 marine terraces. These indicate former stands of sea level, and they're preserved because of uplift. Now, unfortunately, or whatever, it is what it is, but in Oregon, the marine terraces are largely forested. So the marine terraces are not obvious. But I insert this former photograph here to say that if this was an arid area, the marine terraces would be just as obvious as they are on San Clemente Island. It's just that the higher precipitation, more erosion, and the vegetation makes it less clear. However, the marine terraces locally here are well exposed along the shoreline. Probably many of you have been to Boiler Bay. And at these certain areas where there's nicely exposed shoreline, you can see that there's a shore platform, there's a sea cliff, and there's a shoreline angle, which is the indication of modern sea level. And then here you see a very nice marine terrace, which has bedrock, so-called the older rock down here, and then it has beach sands above it. And we'll talk more about these uplifted beach sands and how you can date them later on. Okay, so going back to a local area here, the left panel here shows the entire coastal reach from north of Yaquina Head down to about Beaver Creek. And these colored strips are the surfaces of uplifted beaches. And the color coding is by elevation, so the lowest elevation terraces are in green, they go through yellow up until red. Now the middle panel and the panel on the right are closer looks at the marine terraces north of Yaquina Bay and south of Yaquina Bay. And I'm going to direct you direct your attention to, so each of these black lines that separate these colors are the shoreline, are the paleo sea cliffs, that is the older sea cliffs that are preserved in the landscape. And I'll direct your attention to one of these cross sections, D prime, and this is what this, and there's some vertical exaggeration to this, but this is what these terraces look like from cross section, is that there's the bedrock, which here is gray, and locally it would be a siltstone or sandstone. And then it has the yellow colors are beach sediments with some dune sand on top. That's what without the cover marine terraces would look like. Now let's move on and talk about marine terraces in terms of faulting and folding, what the marine terraces can tell us about deformation. So, and back to our map here. So I'm going to, obviously we're focusing on marine terraces in the general Newport area, but I'm first going to take you down to Cape Blanco right here as a good example of the sort of information you can get from marine terraces and how differently. Somebody asked about the rates, and I'm going to now directly answer your question and say there's not just one rate, there's lots of rates to uplifting these marine terraces. Okay, so this view is pretty easy to conceptualize it once I explain it. Let's suppose you're in a fishing boat and you're about 5 kilometers offshore in the Pacific Ocean, and you're looking east, and you have your geology glasses on, and you're looking at the marine terraces. Well, what you would see is you'd see lots of things. The town of Port Orford is right here, and then south of Port Orford is the old Coast Guard station, which is a prominent headland. But with your geology glasses, you recognize that there are beach sediments above the bedrock here, but these are really, really old terraces. They have old soils on them. And if you were to assess the uplift rate, which is simply the age, how high the terrace is above sea level, divided by its age, we get very, very slow uplift rates, 0.1, 0.3 millimeters per year. But if you go northward to Cape Blanco, and if those of you who are local, you've probably mostly been there, it's a spectacular place. It's a cape that protrudes out into the open ocean. And it has really high uplift rates because a younger terrace has been preserved, and it has uplift rates as high as 1.4 millimeters a year. For a long-term uplift rate, that is over the course of hundreds of thousands of years, that's really rapidly moving along. And not only is it a high uplift rate at Cape Blanco, but you can see how this terrace is folded. And so its uplift rate is high here, and by the time you get going towards Port Orford, the Elk River Valley, the uplift rates drop to zero. So this is what the sort of what marine terraces can tell us in terms of the magnitude of deformation. And we'll use that as we go on to talk. Now, this is an old graphic that was published in the original publication, but it serves our purpose usefully here in several ways. Firstly, the gray areas are these strips of marine terraces that I showed you earlier in a color version. But what I want to show you here is that as of the 1990s, there were two prominent faults that were mapped based on deformation of marine terraces. One was terrace here, Yaquina Bay Fault, and the other one is the Cape Foulweather Fault. Cape Foulweather Fault is basically if you go from Otter Rock over into Lincoln City, in Sluts Bay, you would cross the Cape Foulweather Fault. Now, you can't really graphically see these faults, they're just sort of on a map here, but I'm going to show you a more graphic version of what these faults look like in this picture. Again, take the lower panel. In the lower panel here, imagine you're in a fishing boat, again, 5 kilometers offshore, and you're looking onshore at the marine at the shoreline. You have your geology glasses on as well, and you're tracking the elevation of former sea levels, former shoreline angles, and which you can see as you look to the shore. And let's take the white open triangles for an example. You start here in the community of Yachts. There's not much, and this is the elevation of the shoreline angle or the inner edge of the terrace that was at sea level 125,000 years ago. And this surface has been uplifted, and we're South Beach right about here, and then zoom. Now this terrace is way up there, and this is downtown Newport right there. And it's rapidly uplifting so high that it's mostly eroded, but we know it comes over like this, and then whoop, it drops down as you go over Cape Foulweather, and right in here you're in Lincoln City. So these marine terraces can give you a lot of information about vertical displacement on faults. And this was known back in the 1990s. And so that's where we start when Kirsty McKenzie started to relook at this area again. And so what the graphic I just showed you there would be, this could be presented simply in this block diagram of offset marine terraces. Now, don't be off-put by the alphanumeric cryptic language here. The MIS just means marine isotope stage, and these are assignments of those terraces. Not important, I'll get to it later. But what is important is that the older terrace, the blue terrace, is and the vertical fault is offset more than the youngest terrace, the yellow terrace, along this fault. And that's basically what we see. And you can envision that this fault could be the Yaquina Bay Fault going through Yaquina Bay. But some faults are cryptic, and you'll never see the Yaquina Bay Fault. It's underneath ocean and sand dunes and bay, but that's the purpose of marine terraces, telling you deformations there, but that you can't directly see. Now, I want to shift to a more recent concept about faulting in marine terraces, faulting in the Central Oregon area, faulting on the upper plate in the Cascadia subduction zone, and by considering the case of lateral or strike slip faults. Now, strike slip faults are simply very different than vertical displacement. Vertical displacement faults, do it like that. A simple strike slip fault is a sideways fault. And the most classic example of a sideways fault or a strike slip fault is the San Andreas Fault. It doesn't have much vertical displacement, but it moves on the order of 30 millimeters a year, 30 meters per 1,000 years. So we think of strike slip faults as sort of down there south of us, south of Cape Mendocino, San Andreas Fault. But strike slip faults are a component of the contraction of the subduction zone. Although, of course, the subduction zone is mainly pushing the oceanic plate under the continental plate. There are what's happening in the upper plate can be pretty pertinent to seismic hazard. And a lot of what's happening in the upper plate may be strike slip faulting and not vertical faulting. So I'm now going to go back and revisit our marine terraces again in this local area. And this is the left panel is north of Yaquina Bay, the right panel is south of Yaquina Bay. And and this would be Beaver Creek down here, Yaquina Bay here. That would be Yaquina Head there. So, oh, the corner screen, how about that? What a concept. So the left panel is north of Yaquina Bay. The right panel is south of Yaquina Bay. This would be Yaquina Bay. This would be locally, for those who are local, Beaver Creek, and here would be Yaquina Head. Now, what I wanted to point out here is that the same marine terraces are now color-coded. The yellow is the youngest uplifted marine terrace. The green is the intermediate aged uplifted marine terrace. And the blue is the older uplifted marine terrace. And south of Yaquina Bay, and here, there are older terraces yet still, which are very eroded. We don't know much about them. But note, for example, I'm going to run you through evidence for a different sort of faulting in this local area, and I'm going to do it using these color bandings. And I'm first going to note your attention to the fact that this yellow terrace, the younger terrace, Newport would be right about there. So it's very wide, and the founders of Newport were no fools. They built their marine terrace. I mean, they built their town on the widest and lowest and most flat marine terrace. But if you go across that bridge, the bridge across Yaquina Bay, well, one thing you notice is that you start high in the bridge. You don't have to climb much. You get to the top spans, and you really plunge down to get to South Beach. That's because of the vertical displacement on the Yaquina Bay Fault. But what's also notable is that if you get down, the airport's right here, this area that couldn't be colored because the airport screwed it up. But if you come down here, the lowest terrace is much, much narrower. Well, why is that? Well, the interpretation is that it's narrower because of this sort of concept. Is that, again, we're at the yellow terrace, it's MIS 5A, Marine Isotope Stage 5A, the lowest terrace, and we'll talk about its age soon. And originally, this bill reminded me, I guess can't point at the screen. So this is the shoreline of that marine terrace, okay, this dotted line here. This is also the shoreline of that marine terrace when it was an active beach. Well, of course, before it was deformed, this shoreline was connected across here. But now it's been displacement along this fault, this strike slip fault, such that now the modern wave erosion has waved at present day wave erosion at the base of the sea cliff has equalized out the erosion on either side. But because this side has moved oceanward relative to that side, it has a much narrower band of marine terrace. And that is the evidence for the strike slip component of the Yaquina Bay Fault. Does that make sense to everybody? Or all right, so now I'm going to proceed and talk about some other evidence for strike slip faulting. Now, notice I haven't said anything about how rapidly these strike slip faults are moving, but we'll get to that. But we first need to know ages, which we haven't done yet. Now, let's go back to the same graphic, and now we're going to talk about the green terrace. The green terrace is intermediate in age and a little higher than the yellow terrace. And note that as you go north to south along this panel north of Yaquina Bay, that's all roughly the same width. And then this where my pointer is now, that's Yaquina Bay. And then south of Yaquina Bay, this terrace is really narrow, confined on either side by paleo sea cliffs. And then you get down here to Field Creek, and which is this valley here, and all of a sudden this green terrace gets wider again. And this is, when I initially did this work back in the 1990s, I did not recognize this, and I don't feel embarrassed about it, I just didn't recognize it. I didn't recognize it though, partly because maybe I was stupid, but mainly because I didn't have Lidar. And Lidar is is a technique of seeing the landscape without trees, based on airborne photogrammetry. And Kirsty used Lidar, which is available to everybody now, and she was able to see subtleties in the landscape that were not there before. And those subtleties involved being better able to identify these sea cliffs. So let's go look at the interpretation of the fact we have wide green north of Yaquina Bay, narrow belt of green terrace here, and then south of Teal Creek, a wider belt. So this is the interpretation. Now things have been turned sideways, and I'll walk you through this. But just like initially, I showed you the yellow terrace was much narrower south of Yaquina Bay. That would be a right lateral movement across this fault. But now let's focus in on the Teal Creek fault. And remember, we had a wide green, a narrow green, and a wider green again. The interpretation of that is, well, initially there was this back edge here, this paleo sea cliff was all along the same line because it was all formed when the sea cliff was a continuous feature. But then it was offset by the Yaquina Bay fault in a left lateral sense, on right lateral sense, meaning that you look across the fault as moving right relative to you. And then similarly, you come down to Teal Creek, south of South Beach, and the same terrace is offset in a left lateral sense. That is, if you're standing one side, you look the other way. So this was a major not maybe improvement, but a major revelation is that these terraces not only were offset vertically, like at Yaquina Bay, but they were offset laterally, which strikes us. And so what in the block diagram, it looked like this, is we have these three terraces. They're offset vertically, but this is their paleo sea cliffs, and this paleo sea cliff would correspond to that paleo sea cliff, and this paleo sea cliff would correspond to that paleo sea cliff. So they've also been offset laterally, strike slip fault. Okay, so now that's interesting, but what are the ages of these terraces? Well, one of the other things that Kirsty was able to do with funding from the National Science Foundation is to determine the ages of these marine terraces. In the 90s, we had assigned ages to these marine terraces, and based on well-known histories of the relative sea level fluctuations, but we didn't know really what the ages were. So she was able to test that. And we used a technique called luminescence dating. That was in the title of the talk. And so there's field work involved with this, and this is the field work in part, is we go out to, this is an exposure in South Beach area, and this is the, we're looking at the, we're basically at just above beach level, and looking at the paleo sea cliff for the youngest terrace. And you excavate, you want to get a sample that is not exposed to light, and I'll explain why in a second. So we would excavate this hole, this horizontal burrow hole into the side of the cliff, and then we take a PVC pipe shown here, and these PVC pipes, the diameter was about 3 centimeters, and they were about that long, about 15, 20 centimeters long. And we pound this short segment of PVC pipe into the sand, and then we would excavate out around it and get a sample which was not contaminated by exposure to light. And Kirsty here is proudly displaying one of these samples we collected. And we collected about 20 of these samples. And here's another example of a site where you can see both here is a hole in the beach sands, and here. And these were samples that were collected again at a South Beach site. And in one case, 8.5 meters below the surface, another case, 7 meters below the surface. So why did we collect these samples? Well, I said it was because we wanted to determine an age. And these terrace sands are very hard to date. You've probably heard of radiocarbon dating. Radiocarbon dating only goes back 40,000 years, and you need wood. These sands are older than that, and there's not a lot of wood. But the concept here is, imagine you're a grain of quartz, and you're a happy grain of quartz in the beach, and you're swashed back and forth in the waves, exposed sometimes, not exposed other times, and you're just this happy grain of quartz. Now, time goes on, and you are buried by more beach sand, and you're insulated from the sun. And so at that point, no longer are you a sand grain at the on the beach, which has been basically bleached or removed of all radiogenic material in the grains. But now you can start to accumulate radiogenic elemental material again. And the reason for that is that when quartz grains are buried in the sand, the radiogenic elements, thorium, uranium, uridium, strontium, begin to decay, and they release radiogenic material into the sand, into the quartz grains. And that accumulates over time. You get more and more radiogenic material from radiogenic decay accumulating over time. Now, if a geologist goes out and takes a core, which I showed before, and you take it without light, then you can isolate the amount of radiogenic activity which has been accrued over time in that sand. And then you repeat the process. You take it back to the lab and you zap this thing with luminescence. That's why it's called luminescence dating, which is sort of doing things in reverse. Then you count the number of radiogenic material which has been released to your counter, and you basically reverse the procedure, and then you know the rate at which it was accumulated, and you can get an age. And it's obviously like any lab procedure. It's lengthy, and you have to be a specialist to do it. But that's the general concept. So luminescence ages samples were collected at all the sites where you have these white rectangles. And I don't expect you to read anything on the rectangles, but I will. But this is where these samples were taken. As far north as Beverly Beach, north of Yaquina Head, and then all in the town of Newport, and then at the community campus. One sample was taken right near here in the road up to the community college, and samples were taken down in South Beach. So all over the place on different sites up and down the coast and different marine terraces. Thank you. Yeah, Ka means, where is Ka? The boxes. Okay, and there's also Ka here. I said, no, I got rid of the Ka there. So Ka is a geologist, and Bill knows what it is, but he's wanted to remind me to tell you. Ka means thousands of years ago. Okay, so if you can read that, the white boxes up there, for instance, this sample here came back with an age of 83 plus or minus 14 Ka. 83,000 years ago, plus or minus 14,000 years ago. So we have generous error limits, which is good. So it shows you that we're not just making definitive statements from artificially accurate data. So now here's a summary of the age results. And so the age results confirmed that the three lowest uplifted marine terraces in the Newport area were formed at these ages. Initially, as of this morning, these said 84 Ka, 106 Ka, and 125 Ka, but I changed them for your audience. But anyway, so the lowest three marine terraces were formed at 84,000 years ago, 106,000 years ago, 125,000 years ago. Of course, these are averages of our age determinations, but these ages correspond exactly to the guesses of what I thought these ages were in the 1990s. Not because I'm brilliant at all. It's simply that from explorations in deep sea cores, and not much of that work, some of the support work done right here at OSU and in the Marine Lab here, we determined that these sea level high stands were at these particular time periods because there's a sediment that records high stands which has diatoms and foraminifera, and it's little microcritters that you can date. So these ages correspond to sea level high stands, and they're called marine isotope stages, MIS, because of we use isotopes to determine the age. And so we now know that these terraces we were looking at were formed at these particular ages. And not only that, but if we go back, this is the sea level curve I showed you before. It is specifically these three high stands, the high stand here, the high stand here, and the high stand here. And I threw this graph in again because it's pretty important to realize, more majorly important to realize, there's a definite amount of age difference between 5E high stand and the 5C high stand. Similarly, there's a specific age interval between the 5C high stand and the 5A high stand, and there's also a very specific interval between the 5A high stand and modern. And it's these interval ages that allow us to look at the uplift rates in different time periods. So now we're going to talk about the rates of fault slip on the Yaquina Bay fault and the Field Creek fault. And so just we're all on the same page. We'll make sure that we understand what a fault slip rate is. A rate is simply a distance over time. And a slip rate is how much has a fault slipped over the time interval over which it did slip. And then I give you an example with some real world numbers that are realistic. So you can have a fault that slipped 60 meters, either slipped horizontally or vertically over 120,000 years. And that would give you, doing the simple math, we give you 0.0005 meters per year or 0.5 millimeters per year. That's commonly, so 0.5 millimeters a year would be 0.5 meters per 1,000 years. That's a slip rate. I'll be talking about slip rates, and that's how they're calculated. That's why the ages are important. So first I'm going to talk about Yaquina Bay uplift rates or vertical slip rates. And the Field Creek fault does not have vertical separation, meaning you can't see it in the landscape, and that's why it wasn't recognized until later on with Lidar. But the Yaquina Bay fault has vertical separation, and the average uplift rate in Newport of the Yaquina Bay fault the last 125,000 years is 0.6 meters per 1,000 years. But because we can go these interval uplift rates, that is, we can look at the uplift rate between here and here, between here and here, between here and here, because we have different time intervals and different amounts of displacement, we can say that at one time, the Yaquina Bay fault was really moving rapidly, 1.6 meters per 1,000 years, and that's just uplift, vertical displacement. Whereas other times, it was moving very slowly, 0.1 millimeters per 1,000 years or 0.7 meters per 1,000 years. So there's been, the uplift rate has varied over time. It's just for the vertical displacement. And this really rapid displacement occurred over a period between these two high stands of only about 20,000 years. Now, but what's more important are the lateral faults, the lateral, and don't worry about the small text here. That's just to remind me to say it, but I'm going to focus you on the larger text. But for the Yaquina Bay fault, the long-term strike slip rate is about 1.5 to 4 millimeters per year. And if you look at these interval slip rates between these different high stands, the strike slip rate has varied from a low of 3 millimeters a year to a high for the interval from 106 to 84,000 years of up to 34 millimeters a year. That's a really whopping strike slip. That's the rate at which the San Andreas fault moves. And it's also the rate, although it's a different sort of fault, it's also happens to be the rate at which the Juan de Fuca plate is subducting underneath the North American plate. So not in any sense being alarmist, but just it's incredible to have a fault move at that rate, which is an upper plate fault, which is, sort of a small player. But remember, the data shows it just moved that fast for a certain time period, mainly doesn't move that fast. Okay, well, let's do the same thing with the Teal Creek fault, which is the lower fault here, the lower fault in this panel. And I emphasize the Teal Creek fault has no vertical displacement, so it wasn't initially inferred until we started looking carefully at these marine terrace widths. And again, the small print size is mainly to remind me to say something. The large print size is what you can read. But the Teal Creek strike slip fault has a long-term right lateral slip, and right lateral just means if you're on one side of the fault, you're looking across the other side of the fault, it's moving to the right. Left lateral would mean you're on one side of the fault, look at the other side of the fault, it's moving to the left. It's a real complicated concept. And the long-term strike slip rate on the Teal Creek fault was about 0.1 to 1.5 millimeters per year. But because going back to, I don't remember, I should go back, yeah. But going back to our diagram here, remember that the Teal Creek Fault is really pretty much a weirdo because it moved. Don't point the screen. What am I doing? So, it initially it moved in a right lateral sense, and that's what this. I'm circling the screen now, Bill. I'm doing it right. And then later on, it moved in a left lateral sense. So going back to the text here, so in the earlier period, it moved in a right lateral sense at up to 30 millimeters per year. Well, this is a mind-boggling fast rate of slip, which is comparable to what the San Andreas Fault does, what the subduction zone does. And then later, in the next 20,000 year period, it moved in the left lateral sense about the same amount of distance. So the big print is what you're supposed to read. Note the fault has moved both right laterally and left laterally at rates greater than 10 millimeters a year. So at this point, I'll get to the conclusions, but I just want to, and I'll emphasize this in the conclusions, but this is, I hope this is sounding sort of like the shocking results from the Kaikoura earthquake, because we're having these strikes of faults in the upper plate in short time periods and moving very fast. So in conclusion, the Yaquina Bay Fault and the Teal Creek Fault have both been active in the last tens of thousands of years, and they constitute a hazard as well as a subduction zone. And the vertical slip average for the Yaquina Bay Fault is about 0.6 meters per 1,000 years. But the lateral fault, the lateral slip rate on that same fault is highly variable, but is 10 times faster than the vertical slip fault. So here we had back in the mid-1990s, we published this article in GSA Bulletin saying, hey, look at this this vertical fault in the Yaquina Bay Fault. And wow, there's actually movement on this Yaquina Bay Fault. This is amazing. And well, it was amazing to us, but the world was not shocked or didn't even take notice. But then 25 years later, we're saying, hey, the vertical slip rate's nothing. The lateral fault is moving 10 times as fast, even though the fault's buried underneath the Yaquina Bay. So it's the Yaquina Bay Fault is primarily strikes of fault. The Teal Creek Fault is also a strikes of fault, but you don't see it because there's no vertical displacement. And in the long term, the right lateral slip rate in the Teal Creek Fault is not much, 2 millimeters per year. But the fault has moved both right laterally and left laterally at rates that exceed 10 millimeters a year. We go to the second conclusions. I want to point out that the Yaquina Bay Fault or the Teal Creek Fault may rupture in concert with an earthquake on the subduction zone. And that would be an obvious question to ask, okay, we get a big earthquake in the subduction zone. Do these faults, are they faults triggered? They can be. But neither of these faults would rupture as frequently as the subduction zone does. If these faults ruptured in conjunction with a megathrust, then they have the potential to have co-seismic slip amounts well in excess of their long-term slip rate. And that's what I've been trying to emphasize to you, that in the short term, they can move really fast. And if these faults extend offshore, these faults being the Yaquina Bay Fault or the Teal Creek Fault, then they could pose a tsunami hazard if their offshore portion ruptures the seafloor. And as we can appreciate, the subduction zone is also a tsunami hazard. And I'd like to point out that movie trailers will give you one interpretation of the tsunami hazard, but I emphasize that's a joke, but the megathrust rupture will generate a tsunami. But Oregon has in place many tsunami warnings for realistic scenarios in the event of terms of tsunami height and inundation extent. And certainly they're more informed than movie producers are. So finally, how frequent is a subduction zone earthquake in Newport or an upper plate fault moving with a subduction zone? Well, we know, as earthquake geologists know from many studies up and down the Cascadia subduction zone at different sites, that the megathrust will rupture in an earthquake every 300 to 500 years. And we know because of some sleuthing in the geology record and historic records in Japan, that the last subduction zone earthquake occurred exactly 323 years ago in 1700 AD. So an upper plate faults may move in conjunction with some megathrust ruptures, but not with all of them. And we also know that if you look back in history and time, not just the most recent subduction, but we could go back, there are places in the coast where you can get a history of earthquakes going back 6,000 or 7,000 years. And we know the interval between subduction zone earthquakes has been as short as a few decades or as long as thousands of years. So on a daily basis, a Newport resident would have very little chance of experiencing a subduction zone earthquake. I will project that probably none of you will ever feel one, but a really big subduction zone earthquake. But if you live for the next 2 centuries, a subduction zone earthquake would occur during that extended lifetime. So just in conclusion, and that's the fact about earthquakes here. Enjoy your beautiful coast and move to high ground if you feel seismic shaking, and thank you for your time. And I'm happy to take any questions. I guess that's what
Okay,
you're gonna
time for
say.
questions. Let me run up there with the mic.
Hi, I was wondering with the Teal Creek faults, you explained the difference in the width of the green band, but I was wondering why the yellow band was also still small south of the Teal Creek fault.
So let's start and move forward, and let's start and move towards the present. So, and that's what's happening here. So the blue, this is the blue is the oldest marine terrace. So it formed about 125,000 years ago. And what you're seeing here is the deformation of this terrace before the next terrace was deposited. So at this time, after this terrace was formed, of course, this back edge was straight. There was no deformation, no offset when it originally formed. That we infer from the width just of this terrace that it was left laterally deformed here and right laterally deformed here. Now note that this sort of relative placement of these terraces is not locked in time, because there's more earthquakes that subsequently occur. Now we go back to here in green time. Now in green time, this would be shortly after 100,000 years ago, and initially the sea cliff here was these were not offset. It was one vertical, one continuous sea cliff. But because of the relative widths now, the faulting that's affected the blue terrace has already occurred. But there was also faulting again on these two faults, which right laterally offset the Yaquina Bay fault and left laterally offset the Teal Creek fault. And then if we go to the yellow, the yellow terrace wasn't even deposited when this faulting occurred. But again, the yellow terrace was formed when the sea cliff was right here, but it was a sea cliff that was not offset. And but the sea cliff after the formation of the yellow terrace was offset, but there was only movement on the Yaquina Bay fault in a right lateral sense. And that's why you have a wide terrace that Newport's on and a narrow terrace further to the south. So in that long answer, did I answer your question? Well, yeah, each of these are a slice of time. The reason these arrows would seem seemingly confusing is this is a right lateral fault, now it's a left lateral fault. These are time slices showing what this fault did at this time. And so it makes sense, it can make sense that this fault moved right laterally after 125,000 years ago, but after 80,000 years ago, it moved again, but it moved left laterally. And that's the whole point here is, one of the points is that these faults, they're just there's this big subduction zone, and which is about 25 kilometers below us, and it's this big honking fault. It's just sort of doing like and going like this with time, and every once in a while it ruptures. And then there's these upper plate faults, which are shorter and which are responding to minor, relatively minor changes in their strain habits because of what's happening down below. So they're just responding to whatever happens to be the strain on them at the time. And it can vary from one time to the other. And that was one of the fascinating things about what Kirsty did here. She recognized the fact that these upper plate faults, and she goes into more detail on this, but if you look in detail at what might be happening in a subduction zone, they're not always stressed the same way. And so you can get these reversals and slip.
So I actually have a question on the same slide. So I didn't catch before that the Yaquina Bay fault had also moved in both directions, left lateral and right lateral.
Yeah.
So they both have.
They both have.
And do you know other examples of other faults that have done that in the world?
Yeah,
That
well,
sounds
Bill asked you,
crazy.
I know examples of other faults, and that's the interesting thing between seismologists and earthquake historians who look at the modern earthquakes when they occur and looking at the record of earthquakes. Is it no? I don't know of any other. I don't know of any other examples of this.
Like the San
modern-
Andreas always goes in one direction.
What's that?
San Andreas doesn't change.
Well, but the San Andreas is a plate boundary.
Yeah.
Okay.
yeah.
So
it's
San
different.
Andreas is hugely different. San Andreas is hundreds of kilometers long.
Right.
These faults are tens of kilometers long.
Right.
So, but
Okay. Let's try see if there's one online, a question online.
Yeah, this is a two-part question, and I'll read you part one. Do you think the Yaquina Bay and the Thiel Creek faults move only during megathrust earthquakes, or are they potentially earthquake hazards as well?
yeah, and then to
Good
rephrase the question, are the Field Creek fault and or the Yaquina Bay fault seismic hazards in and of themselves without having the subduction zone move? And the answer to that is yes, they could be. There's no reason. However, if we use the Kaikoura earthquake example, we've now learned from the Kaikoura earthquake and the Chilean earthquake and another earthquake in New Zealand that you can get upper plate faults that move in conjunction with earthquakes or not. In the case of the 1960 Chilean earthquake, really looking at records, there have been strike-slip faults that occurred at the same time as the mega. 1960 Chilean subduction zone earthquake is the largest earthquake recorded. But there was also an earthquake that occurred in New Zealand, in the North Island, which had the largest strike slip that's ever been recorded anywhere, and it was on a fault that moved without the subduction zone. So help me, Sue, what was the name of that fault? The Wairarapa fault. So
it could be either.
it could be either, yeah. And it was the second part of the question?
Oh, yeah.
Here's the second part. Does Alsea Bay also potentially have an east-west tending fault? Alsea has the same general morphology as Yaquina Bay, with the ground on the north side and lower elevation on the south side.
Yeah, very good question. Based on the marine terrace work that was done back in the mid-90s, the answer is no, it doesn't appear to have. There's several faults that offset the wave cut platforms, but interestingly, there are north-south trending faults. But if you look at the overall, I think maybe even I can show this. I think it's on this slide here. Yes, there it is. Okay, so this is Alsea Bay is right here, and the you can see that in Alsea Bay that these at least in the offset of the terraces, there doesn't seem to be much offset in this white triangle area. But you get to the older terraces, and these are quite old. You can see there's there's all sorts of deformations going on in Alsea Bay. Notice how there's a syncline right there, and there's another syncline right there. And I call it the Alsea Bay down warp. So something is happening in Alsea Bay. We don't understand it as well. There's no evidence now that there's an east-west fault, but certainly there's deformation.
Okay.
Perfect slide. This is exactly what I noticed is that, the Cape Foul weather and the Yaquina Bay fault, and I'm assuming probably the Thiel Creek fault as well, appear to be roughly parallel in direction. And I also noticed from, you know, the subduction zone that it seems to be perhaps moving in such a way that these faults are, you know, essentially perpendicular or not?
Okay,
Why
so
are they parallel, and does it have to do with the subduction zone, to try and cut the
Um,
question to the chase?
so it's hard to draw a line when you only have one point, right? And so I really don't know what the trend, as the geologists say, or the strike of the Yaquina Bay fault is, or the Cape Farewell fault. Although I've depicted them on here as this particular direction. And this direction is roughly perpendicular to the trend of the subduction zone. What I can say is that there was a lot of geologic mapping that was done in this area here 3 or 4 decades ago now by a man named Park Snavely, who worked for the Geological Survey. And he mapped a lot of faults in the, quote, bedrock. The bedrock's not very old. It's 30, 40 million years old, but it's older than marine terraces. And a lot of the faults were roughly this direction. But we know very little about the Yaquina Bay fault in terms of, I mean, I'm speaking up here as a geologist telling you it exists, but we don't know its direction. And it's because it's entirely buried by bay water or bay fill or sand dunes, but it has to be somewhat in this direction. But and actually, I know more about the faults around Kelsey Bay and Goldport because I could see the marine terraces are offset in several places. So a long-winded answer to your question is that these are guesses. They have to be more east-west than north-south.
Okay, we're running pretty long on time, so I think we're going to end it here. And if you have more questions, you can come up and ask in person. So let's thank Harvey for a great talk. Thank you.
Over.
And Harvey, how can our folks reach you via online? Do you have an email that you'd like to share or contact information that we could put on the chat?
Contact info you want to put in the chat for online questions?
Sure, I'll put my email address in the chat.
So we'll
Thank
do
you.
that. All right. Thanks, everybody.
How do I get to the chat?
No.
Actually, I should turn this thing off now. Shouldn't
You must be thinking about Long River salts.